In this section, we're going to look at the graphs of both the sine and the cosine functions. So let's talk a little bit about the domain and range. The domain of a sine function, which again, reminding you, for both sine and cosine, when we talk about domain, we're talking about values we are allowed to plug into the function without it becoming undefined or resulting in numbers that are not real. And for both sine and cosine, the domain is all numbers negative infinity to positive infinity. There are no restrictions on what we can plug into both sine and cosine. The range of the basic sine and cosine functions is -1, including -1, up to +1, including +1. Of course, sometimes we'll do stuff to these functions, but if we're just talking about sine x and cosine x, those are both domain and range of those functions. A periodic function is a function in which we see a repeating pattern of the outcomes. And that is definitely something that we have with the trigonometric functions. A function f is said to be periodic if there is a positive number p such that if we add p to x, eventually we get f of x for every x in the domain of f. In other words, we get to a certain point and it repeats back to what it was before we added p. The smallest value of p, if there is one, for which f of x plus p is f of x, is called the period of f. The period basically is the amount or the value it takes for us to begin repeating our cycle. The graph of f over any interval of length p is called one cycle of the graph. And we'll see this visually as we examine the graphs of these functions. So with sine and cosine, for any real number t, so any starting point, if you add 2 pi to it, you will see it repeat back to the sine of t. Same with cosine. So for any starting point along here, when we add 2 pi, we see a repeating function. And so with both sine and cosine, again, the basic sine and cosine functions, not anything being multiplied inside, added, or subtracted, or anything like that, will always have the period 2 pi. So what are some of the properties that we see with the sine and the cosine function? A few of these we've discussed already. Domain of both sine and cosine are negative infinity to positive infinity, our default values for our domains. And then our ranges go from -1 to +1, -1 to +1 for both. Keeping in mind what sine and cosine are. They are points along the unit circle, meaning the radius of the circle is 1. X represents the cosine values, and sine is the y values. So, cosine values, x coordinate, sine values, y coordinate. Which takes us to the next property when we talk about sine. Remember, sine, of course, is our y values. So, the sine values are 0 at t equal to n times pi. N is any integer. So for describing the zeros of our angle for sine, they're going to happen. Remember, sine represents y. Y has a 0 value here and here. So at any pi, 2 pi, 3 pi, 4 pi, and of course 0 works there too. 0 is an integer as well, so if we plug 0 in here, we get 0 times pi, which is 0. So these are where the zeros of the sine fall. For cosine, which is our x, we see zeros here and here. This is where x is equal to 0 at the y-axis. So we have pi over 2, which remember pi over 2 is 90 degrees in radians, plus n times pi. If we go pi from there, we're here at 3 pi over 2. And then back around again, and we can even go in reverse as well for any integer. When we look at our maximum and minimum values, remember the radius of the circle is 1. So as high we're going to go is positive 1, low is negative 1. And for sine, remember, keep in mind sine is y. We have our high point and our low point here and here. So just like the zeros for cosine, that's where we have the minimum and maximum values for sine. And for cosine, x equal to 1 and negative 1 happen here and here. So where sine was equal to 0. So at we get 1 and negative 1 at t, cosine of t, at 2 pi n, so here, and then plus pi more. Or 2 pi more, sorry. That would give me 1 and negative 1. Sine is an odd function because if we plug a negative in, we get a negative outcome. So for example, for sine, if I go up to here, I'm at positive 1. But if we had gone in the opposite direction, negative t, I would have ended up at negative 1. So the outcomes are the opposite for the same input, but with a negative. With cosine, if I go, and remember, cosine is the x value. So the x value is at 1 here, right? We're at 1, 0. If I go up t units, so I'm just going to go to some random place, where it's 0 is helpful because x would be 0 here. If we look at the opposite, if I'd gone the same distance but in the opposite direction, I'd be here, which has the same x outcome as this did. These both have an x outcome of 0. And in fact, let's say I stop halfway up here. This has a certain x value. If I go the same direction down this way, we have the exact same x value. They correspond. So a negative t gives me the same output as positive t with cosine. And both of these have the same period, meaning they repeat every time we've gone around the circle one time, right? So they repeat at every 2 pi. That is the period of both the sine and the cosine function. So what does the graph of the regular sine of function look like? What is it? How does it appear? And you can see it down here in this wave. It's basically like a wavelength. Sinusoidal curves always have this sort of cycle in the way that they move. So let's take a look and make some sense out of this. First of all, thinking about sine of x is 0 at 0, right? Sine is the y value. So we start out at 0, 0, which is the intersection here. And then by the time I get up to here, I've hit a maximum value of 1. The y value at 90 degrees, or pi over 2, is 1. So we can see that this is the curve right here. And then if I keep going over to pi, I'm back to 0 again. So we have this falling value here. And then when we go to one more 90 degree or pi over 2s, so we're at 3 pi over 2, we're at negative 1. That would correspond with this point of the curve here and this point of the curve. And then by the time we've gone all the way around, we're back up to 0 again. And so within this area here, we've done one cycle. And so this would be my period. My period is 2 pi. It repeats every 2 pi. And we see it going again. That's the graph of the sine function. The cosine function is very similar as well. If you look at it, the cycle that it has there is pretty much indistinguishable from the previous. The only difference is where the high points are for the cosine. Remember that here at 0, our actual value there for cosine is 1. 1, 0, 1 being the x value. And so our curve is starting here at 1 rather than at 0, 0. So we're at 0, 1. By the time we've got up here, we're at 0. And so at pi over 2, we're at 0. By the time we go back here, we're at negative 1. So that's when we hit pi. And by the time we get to the third, we're at 0 again, 3 pi over 2. And then heading back up here, we end our cycle at 1. So we have one cycle going from 0 to, just like with sine, 2 pi. But if we only looked at that, it would look more like kind of a U shape here. Same graph, but starting at a different place. So it's been shifted. So you can see, looking at that previous side, that we have some very key points along our curve. We've got our starting points. We have our high points, x-intercepts, which is the same as our starting point there. We have our low points, and then we have our x-intercepts. So x-intercepts, high points, kind of define what our graph is going to look at like. So if we can discover what the x-intercepts are and what the period is of our function, those are things that can be very helpful for us in graphing the iterations of both the sine and the cosine function. So getting some clarity on a word I used just a little bit ago. The graphs of both sine and cosine functions, they're called sinusoidal graphs or sinusoidal curves. Both of them are. You have sine and cosine, right? Cosine involves sine. So in other words, the functions y equal a sine x and y equal to a cosine x have an amplitude, absolute value of a. And the range will go from negative absolute value of a to positive absolute value of a. We have to put the absolute, because sometimes a can be a negative value. And so the amplitude is something that's always positive, right? So if it's negative, that's going to flip it across the curve, just like we've seen before with other functions. And so at any rate, we're looking now at how a is going to impact the curves, and what it impacts is the amplitude, which affects the range, so how high and how low they go. And remember, the highest output of cosine of x is 1, and the lowest is negative 1. And so if I take the highest outcome and the lowest outcome and multiply that by a, we can see really it's just affecting how high it goes. So instead of stopping at 1 and negative 1, we would stop at positive a and negative a. So since we can see that the value out front, if we multiply sine by a number, a, we'll say, that we know that a is going to affect the amplitude of the function, and we will see the amplitude affected by the absolute value of a. So let's take a look at just the regular sine function. We're going to sketch it really fast. Remember that y is at 0, 0 for sine. And once we go 90 degrees, we're usually at 1. And then we go to pi, and we're at 0 again. At 3 pi over 2, we're back to negative 1 now, and then back to 0. So here's a graph of our sine function. And that goes the same, the pattern goes the same in the negative direction. Negative 1, 0, positive 1, back to 0. All right, so if we multiply it by a third, so my a has a value of 1/3, the only way that's going to affect my graph is it's going to affect how high it goes. At 0, we are still at 0. But here we're only going to go up to a third, so which is a little less than a half. Still at 0. Down a third. Back to 0. So third. 0, 1/3, and back to 0. So here we have our graph here when A has a value of 1/3. We can see it as before, condensed it vertically, compressed it vertically. Just like you can see the whole patterns that we've had since we've been doing this. And multiplying it by a value that's higher than 1, such as 3, stretches it vertically. So we go up, we go down, down, and back up. Down, up, up, and down. All right, so this is kind of the more obvious, easier one to take account of, because it does what we've always had it do. It always stretches it vertically or compresses it vertically. And that we call, in a sinusoidal function, is the amplitude. In looking at the graph of cosine, cosine, again, starts out, it's our x. So at 0, it's actually at 1. So I'm going to write these in here. 1, 2, 3, -1, -2, and -3. And then let's graph the cosine function here. So we know that at 0, we have 1. The cosine of the x at the 0 is 1. Then we go to 0, then we go to -1, back to 0, and then up back to 1. You really want to try to smooth these over as you go through these points. You should not have pointy points. They should be reaching a height, right? And so if I continue this in the opposite direction, we see that same pattern continue. Our period, we have two periods here. We went from -2 pi to 2 pi. So our periods are from here to here. And this is one period, this is two periods. 1 and then 2. But so when I multiply by negative, obviously it does a couple of things. Negative, of course, is going to reflect it across the x-axis. But then the negative part will negate it. So normally if I multiply it by 2, this y value would simply be up here, the first one. I'm going to switch colors here. And we would continue in that same power, just be stretched. But with it being negated, it also needs to do the opposite. And so we can kind of look through here and see how this would be the opposite and amplified at the same time. So it takes a little practice to graph these and make them smooth, but that's what you want to practice as we graph these by hand. Again, to 0, up to 2, 0, and back down to -2. And again, we have two periods here that we've graphed for our cosine function, both for the just regular where the a value is 1 and when it's -2. So we negated it, and then we also, I think I didn't go down far enough here. Actually, I went too far here. Sorry about that. But so yeah, this would be a little bit lower. This one over here was right, but then this would end right here. All right. So at any rate, that's the graph we have with cosine. Both one period each. And so this would represent two periods, -2 pi to +2 pi. So the multiplying it did not affect my period at all. It simply affected the high point and the low point of the curve. Now that, of course, is multiplying the outcome, multiplying the sine of my x. What happens if we multiply the x before I've taken the sine of it, which is what we would do here with this b? So we're going to let b represent any number that's being multiplied by the x before we've taken the sine of it. So we're going to do these same ones, but notice that the number 3 in this case is actually being multiplied by x. So it's not 3 sine x, it's sine of 3 of x, and sine of 1/3 of x, and sine of x. Well, sine of x just doesn't have any b there. Well, the b is 1. Let's say that. So how does that affect our graph? That is going to affect its period. And so the way it does, we'll take a look at that here. Remember how when we do things to x, it kind of does the opposite of what we think it will. And by multiplying the x before we've taken the sine of it, it is going to stretch and compress it, but it's going to do so in a horizontal way and in the opposite way that you would think. Normally, you'd think if we multiplied, we would get a larger period, but in actuality, we end up getting a shorter period if that number is greater than 1. If the number is smaller than 1, we end up getting it stretches it horizontally. Begin with the curve y equal to sine of x and divide the period. Remember, the period of both sine and cosine is 2 pi. We're going to divide that by 3 to get our new period, 2 pi over 3. That's our period for y equal to sine 3 of x. One cycle then of y equal sine of 3x will be compressed. So notice we multiplied it by 3, and it compressed it into a smaller interval going from 0 to 2 pi over 3. If you remember, 2 pi over 3 is 2 pi over 3s. Pi over 3 is 60 degrees. Pi, remember, is 180. 180 divided by 3 is 60. And so 2 of those, 2 pi over 3s, is 120. So our period now went from 360 to 120. We divided it up by 3s. And so how do we figure out our key points? Our key points are going to be the points that we hit basically we're going to divide it up 4 ways. So if I have 2 pi over 3, and this is my period, if I want to divide that up evenly, 4 ways, we just multiply it by 1/4. You notice 2 goes into 4 twice, and so that leaves me with pi over 3 times 2, or pi over 6. So pi over 6 represents 1/4 of my period. If you remember, pi over 6 is 180 divided up 6 ways, so 30 degrees. So my period is going to go from 0 to pi over 6 to pi over 3 to pi over 2. And then finally, 2 pi over 3 is where our cycle completes for our sine function. So that would be the period, or what have you, for y equal to sine 3 of x. In a similar way, to find the period of y sine of 1/3 of x, we're going to divide 2 pi by 3 by 1/3. That should be by 1/3. Let me just put that in there. By 1/3. So we take, let's just go ahead and erase this. We're going to take 2 pi and divide it by 1/3, which is 2 pi times 3 over 1, which is 6 pi. So 6 pi now is my period. So it got actually pulled out, horizontally stretched, when I divided it or multiplied it by 1/3. So again, it's the opposite of what you would think when it happens to x. So our interval is from 0 to 2x. with these x-coordinates for the key points. Let's think about the key points there. If we want to take 6 pi and divide it by fourths, we're going to multiply it by 1 over 4. That would give me 6 pi over 4, which reduces down to 3 pi over 2. So each period, or each quarter of a period here, is going to be 3 pi over 2. So we'll start off with 0. 0 would be my first point, right? This is kind of our starting. So we usually end up with 5 points, right? We've divided them 4 ways, but we're starting at 0. And then the next key point is going to be at 3 pi over 2. And then the next point is at I add another 3 pi over 2, which would be 6 pi over 2. I'm going to write that over here. 6 pi. We add another, 6 pi over 2. So that would be 3 pi. And then to 3 pi, we add another 6 pi over 2. So let's take 6 pi over 2 before we reduced it, add another 3 pi over 2. And that gives me 9 pi over 2, which doesn't reduce. And then if we have 9 pi over 2, and we add another 3 pi over 2, that gives me 12 pi over 2, which is my endpoint there, the end of the period, 6 pi. So sometimes it helps to keep them in the form y over 2 or pi over 2, because when you're adding, you've got to have that similar denominator, but always pay attention to when things reduce down. So we go from 0 to 3 pi over 2, which would be 270. Then we go another 3 pi over 2, which takes me to 3 pi. That would be 180 plus another 360. So, whatever that is. 480, 180, 360, 5 something. And then back around again to 9 pi over 2 and then 6 pi. So, at any rate, that would be the 5 key points there. But we would pattern them after the sine curve. And I'm going to show you how to do that in a graph. All right, so let's take a look at the first one where we had y equal to sine of x, and then we are going to compare it to the graph of y equal to 3 of x. I've adjusted this a little bit so that we're really just going from 0 here and then forward along there. So I'm going to put that in there, but just notice that I changed this so that the middle, at least it's supposed to be just another gray line, that my starting point at 0 is actually over here. And then we have our periodic curve from there. So we're just going to focus on that. And for a lot of these sine and cosine, mostly the sine and cosine functions, this is how I like to do it. And then I can just adjust where I'm putting these on. And so graphing paper can be a really helpful thing for you in practicing graphing these. But let's go ahead and start with our first, which is just our regular y equals sine of x. We know y equals sine of x starts at 0, because at 0 we have 0. And then we go up to 1, and we go back down to 0, we go to -1, and then we go back up here. And so I've marked these out so that each thing going up to the 1 is actually, each unit is a quarter. So 4 of those take me all the way to 1. And then we're going down here, where I'm not crossing the y-axis there. That's not the y-axis, but rather the just another point along the curve. All right, so there's our sine function for one period from 0 to 2 pi. And we're just going to see how that compares when we multiply by 3. Remember that when we multiply by 3, that takes 2 pi and divides it by 3. So instead of 360 being my full thing, or 2 pi, we now have 360 divided by 3, which is 120. So the whole period ends at 3 pi over 2, which is right here. So this is going to be my ending point here for the new sine curve. And we've divided this up by 3s. So at any rate, we took let me do this down here in blue. We have 2 pi, oops. We have 2 pi over 3, right? And we multiplied that by 1/4. 2 went into 1/4 twice, so that gave us pi over 6. So pi over 6 was my one thing. Each thing, if we divide it up 4 ways. So at pi over 2, pi over 6 is equivalent to 30 degrees. You'll notice this is 90 degrees. So we have 30, 60, 90. So our first thing is at pi over 6, which would be here. And then the next thing would be pi over 3, which is 60. That's right here. My next thing is pi over 2. Notice what's happening here is I start out with pi over 6. I then added to pi over 6 another pi over 6. That gave me 2 pi over 6, which reduces down to pi over 3. 2 goes into 6 3 times. And then we had 3 pi over 6. So I added another pi. That gave me 3 pi over 6, which reduces down to pi over 2. And then I added another pi over 6, which gave me 4 pi over 6, which is 2 pi over 3. And 2 pi over 3 then is my another one here. So this happened at 120 degrees. And so let's see how this works out in terms of this is my first. We're following the same pattern. We haven't changed the pattern. We've just we've compressed it horizontally. Because we multiplied by 3. And when we do anything to x, remember it just so happens to do the opposite of what we would expect. We multiply by 3. It basically cut this into thirds. If I kept this pattern going, this would go up again, and I keep on getting that ridiculous line. We'd go up here again, down, down, up, up, down, down, and then up. So I think I made an earlier thing. I said the wrong thing. So I just want to point that out. This 3 pi over 2 was not the end point. It was 2 pi over 3. I had that backwards. So anyway, I erased that. But you'll notice that now I've been able to get 3 periods in here. Oh, that line. So where I had 1 before, now I have 3 full periods. The first one ending here, the second one ending here, and then the third period ending at 2 pi. So it actually tells me, comparative to the original graph, to the parent graph, how many periods now I will have between 0 and 2 pi, that multiplication by 3. Interesting enough. Now let's take a look at what happens when we are multiplying x by 1/3. So I went ahead and I drew in the regular sine curve. Notice that I've completely changed my units here because I already knew what was going to happen. Rather than it being compressed, it's actually now going to be stretched. In other words, we took 2 pi, we divided 1/3, which really took 2 pi and multiplied it by 3 over 1, which gave me 6 pi. So that's going to give me 3 rotations, right? 6 pi's, 3 rotations, 2 pi 3 times. And so I needed to compress my units so that I could stretch it out or portray the stretched out. So, and what did we find when we divided by 1/4? We took 6 pi, we multiplied it by 1/4. That gave me 6 pi over 4, which is 3 pi over 2. So 3 pi over 2 is each rotation. So I'm going to start labeling here, remembering that every time here, I'm going to be adding 3 pi over 2 to its next period. But if I just kept going here at 2 pi, I've got 2 pi, and then we're adding another pi over 2, because my units here, you can see, are pi over 2. One more pi over 2 to 2 pi. If we take 2 pi and we add another pi over 2 to that, we get 5 pi over 2. So 5 pi over 2 is my next thing here, which that doesn't reduce. But if I add another pi over 2, that gives me 6 pi over 2, which is 3 pi, which is the same as 6 pi over 2. If I added another pi over 2, it would be 7 pi over 2. Added another pi over 2, that would give me 8 pi over 2, or 4 pi. But 8 pi over 2 plus another pi would be 9 pi over 2. Plus another pi over 2 would give me 10 pi over 2, or 5 pi. And then 11 pi over 2. So you don't have to mark all of these out, but I'm kind of just doing this. And since I started it, I'm going to just keep it going here. 12 pi over 2 would be 6 pi. And so that represents my end here, 6 pi. But the main one that I needed to focus on was, for this graph, we're starting at 0, and then we're going to hit 1 at 3 pi over 2. And then I want to go 3 pi over 2 more. And so we actually had those written out on the previous page. But we started out at 0, and then we went 3 pi over 2. Then we added another 3 pi over 2, which gave me 6 pi over 2, or 3 pi. And then added another 3 pi over 2 to 6 pi over 2, which would give me 9 pi over 2. And then we added another 3 pi over 2, which added to that gives me 12 pi over 2, which is 6 pi. So marking those special ones out, we've gone 3 pi over 2 every time. Those are really the ones that we have to take note of. So let's see. So we're at 3 pi over 2. Then we need to go to 3 pi, which I believe actually is here. And I think I marked it wrong. I did. I meant to put 6 pi over 2, but I put 3 pi over 2. But 6 pi over 2 is what it is. But if you divide 6 by 2, it's 3. So that's my next 0 there. And then we had 7 pi over 2, and then 9 pi over 2 is where we're going to hit -1 here. That's my next one. And then back up to 6 pi. So really, you can the key to doing this is adjusting your units each time. And I know that it gets a little tricky at times here when it comes to, what is 3 pi, and getting used to adding fractional values to that and such. But generally, you have to remember with fractions, we want to keep them with the common denominators. So they may not be reduced all the way, but it makes them easier to add when we keep that 2 in the denominator in this case, or what have you. So let's summarize what we found here. The functions y equal to a sine bx and y equal to a cosine b of x, where b is greater than 0, have amplitude a, right? That's how high they go, the amplitude, and a period of 2 pi divided by b, whatever the value in front of x there, that's what we divide up 2 pi by. If a is greater than 0, so the period, I'm sorry, not the period, but the amplitude is greater than 0, the graphs are similar to the graphs of y equal to sine and cosine. With 2 changes, the range is now -a to +a. One cycle is completed from 0 to 2 pi over b. And the x-coordinates for the key points are 0, and then we add pi over 2b to each time. The y values at each of these numbers is either negative a, 0, or a. Right? Those are our key points, the high points and the zeros along the way there. I just want to take a second here to look at how we got these numbers here. Remember that this is my new period here, 2 pi over b. So, and there's going to be 4 stopping points there, right? So we're going to take 2 pi over b, and we're going to multiply it by a fourth because we want to divide it up into its 4 stopping points. That gives me pi times 1 over 2 times b. So this is what I add each time. So starting at 0, we add that, we get that here. And then if I take that, pi over 2b, and add another pi over 2b, that gives me 2 pi over 2b, which the 2's cancel out, so we get pi over b, which is what I have here. But before that, it was 2 pi over 2b, so if I add 2b, and I left that there because I want to add another pi over 2b to that, and so that would give me now 3 pi over 2b, which doesn't reduce, and that's what I have here. And if I add another pi over 2b, that gives me now 4 pi over 2b. 2 goes into 4 twice, so that's 2 pi over b, my final thing here. So I know they throw all these things here. You're like, oh, I have to memorize that? Not necessarily. This is just the, you can, but this is just what we were doing before. But I was doing it with real numbers and not variables there. Regardless, here's kind of a general picture of how this is composed of. We're going from 0 to whatever, 2 pi over b, and this is how we can always graph our equations. Our amplitudes go here, and we divide it up 4 ways, so we have to figure out what they are, and then we draw the sine pattern through those 4 points, right? So we can adjust our x-axis and the y-axis to whatever numbers we want. And so they kind of look the same. So the key parts that change from graph to graph to graph are the values along my x-axis here, because that's determined by my period. The only thing different about cosine is the way that the cosine curve plays, right? It starts out at 1, or whatever the amplitude is, and it goes through the 4 points, just like with sine, but in just a shifted way. And so we're just displaying, really, the new period and how we divide up that period in 4 respectful ways. And sometimes it helps to think about the degree difference in what we're adding there, and at least attaching it to the equivalent with radians. All right, so let's look at an example. Here we've got 2 things happening. We've got a 3 out front here, and then we're multiplying x by a half. So what is that going to do? Well, first of all, we know 3 is going to raise my amplitude. So it's going to go up higher and down lower. My range now is going to be from -3 to +3. And then multiplying x by a half is basically going to double my period. So we're going to take what would be the normal period of 2 pi for a regular function, and we're going to divide that by a half, which is the same as 2 pi times 2 over 1. So now my new period is going to be 4 pi. So that is my new period. My period is 4 pi. And we're going to divide that period into 4 quarters, that period of 4 pi. My amplitude, sorry, I didn't write that in there, is 3. So let's divide that into 4 quarters. So if I go 4 pi and I multiply that by 1/4, we see that each thing is going to be a pi. So we're going to just add pi each time. So starting at 0, I go 0, and then pi, and then 2 pi, and then 3 pi, and then 4 pi. So this is actually a really nice, easy one because it doesn't have any denominators for us to deal with. So those are my 4 quarters there. So the 5 endpoints give the highest and lowest points and the x-intercepts of the graph. So let's look at graphing it. Okay, so on my curve, you'll notice that I've just marked out 3 and -3. That's my amplitude. You can put it the same place you would normally put 1 if you wanted to do that. However you want to do that, remember you're controlling the units along the y-axis. So it's not cheating or anything to do that. And then what we have to do here is just mark out however I want to. I could have gone every third, but I just went every other. I'm going to go pi, and then we had 2 pi, and then we have 3 pi, and then we have 4 pi. All right, the 4 starting points, and then, of course, 0 as well. And then we're just going to go through and draw out our curve, starting at the high point, going down to the low point, back up to 0, and then back up to my high point. Connecting those dots. Oops, my high point should be here. Let me fix that really quick. Hopefully it doesn't erase this whole thing that I just drew. Yeah, okay. Good. I thought that was a little strain there. All right, so there's my graph for the cosine. I've adapted it. I can see by the values along the x-axis that we basically doubled the period because I divided by half the b for this function. Next up, we're going to look at what happens when we subtract c. So we subtract something from the x before we've taken the sign of that. Historically, we have seen exactly what happens there. It always shifts my graph horizontally. And it does so with the opposite of what we see. So for example, here we have y equal to the sine of x minus pi over 2 over a 1 period interval. And we're going to graph that. And so we know that since we're subtracting pi over 2, that actually affects it in the opposite way. It's going to shift it to the right pi over 2 units. So the graph of f minus c, notice when they put minus c in, so the minus with the variable c, so c being the amount that it's being subtracted, that when c is actually positive, then it's going to move it in the opposite from what we see. Minus a positive will still look like minus positive, but the c value is how we're adjusting it. So whenever we have a minus in front of a variable like that, that's when it shifts in the opposite direction. I just want to recognize that. So it shifts to the right c units. That's when we see minus c. That's if c is positive. But if c is negative, then when we plug c in, minus a negative looks like plus a positive. Minusing a negative looks like plus a positive, and so we end up shifting it in the opposite again to the left c units. So with the x minus pi over 2, that's taking my blue graph here and shifting it to the right. Everything else remains the same. The amplitude, etc. just moves everything pi over 2 units to the right. So combining that with everything else that we've looked at so far, with our amplitude, with b affecting the period of our graph, and now c affecting the horizontal position of our graph, when it's in this form, and one thing I want to point out here is that b, which is on the inside of sine here, has been factored out of whatever we have with x here and our subtraction. Or addition, doesn't really matter, with both cosine and sine there. To find the amplitude, period, and phase shift, we're going to look at my amplitude. That's my a there, take its absolute value. That's the highest and lowest point of the graph. The period will be 2 pi divided by whatever the b value is after we've factored it out. and the phase shift c. That's going to shift it to the left or to the right. The starting point for the cycle is at x equal to c. Then the interval over which one will complete the cycle occurs is c. Notice that's the value that's we are identifying here, plus my period, 2 pi over b. Once we figure that out, then we're going to divide that interval from c to, c plus that. So that's the c value is, of course, we've shifted it c units. So that's where instead of just being at 0, we have to add c there into 4 equal parts of equal length. So we're going to take 1/4. That's how many parts we want to divide it in, and we take this, and then we're going to add that result to c, and we do it several times to get our 4 main points, c plus, and then again, again, and again. Of course, pairing up these new points that we found with their values, we're going to start with c, and that's our 0 point, and that's for a sine function, because sine always starts at 0. We'll be at starting there, and then adding our new period, a, new period 0, new period negative a, and then 0. So really we're just denoting here that whatever a is, the new amplitude, that'll be our new points at these key values along the way. For cosine, of course, it's a little bit different because we start up at whatever our amplitude is. Usually it's at 1, but if we have something else out here, it's going to start at that point, then go to 0, then negative a, then 0, and then back up to our a. Again, these are not things we have to memorize, right? The process we want to memorize is, first of all, what do the graphs look like for sine versus cosine? Second of all, be able to calculate the new periods with the shifts in the amplitudes, and then sketch it out, noting along the x-axis my new points. We also want to keep in mind, of course, the situations where a is negative. In the case of a, the number out here being negative, remember that reflects the graph across the x-axis. And so it'll be the opposite of whatever we would have if it was not negative. So the absolute value of a there was the case, then this is going to be the opposite of that, reflected across the x-axis. So let's look at an example with a cosine here. We have the negative cosine, and we have a 2 here. And we have x plus pi over 2. Remember that in the general formula, it's x minus c. And so when I'm looking at c and I see x plus pi over 2, I'm thinking x minus negative pi over 2. Right? And that makes doing the opposite thing a little bit more something to remember there, because the c value is actually where we're going to start. But if all we see is x plus pi over 2, we begin to mistake the idea that my c value is pi over 2 and that it's positive, so we move to the right. The c value is actually negative, right? Because in the general formula, it's x minus c. And if I have plus, that means I have minus negative. And so we're starting actually at negative pi over 2 as our starting point. All right, so filling out the rest of the information there, the amplitude A is -1, and, well, the value of A is -1, and so the amplitude is just 1. And it's going to be, we're going to go up to 1 and down to -1, but that's our amplitude. But it is negative. We want to take that into account. The period is going to be 2 pi divided by my b, which b here is 2. And so my period is actually pi, which I will have to divide up. And the phase shift, I've shifted it negative pi over 2, or pi over 2 units to the left. So I can say that C here is equal to that pi over 2, negative pi over 2. So the value of C does indicate the direction, right? But the value of C always needs to be looked at as whatever the opposite sign is from what we see here. We see positive pi over 2. The value of C is actually negative pi over 2. And so my cycle will be graphed starting at negative pi over 2. And we're going to add pi to that. And if we add pi to that, negative pi over 2, that gives us positive pi over 2. So we're going to graph from negative pi over 2 to positive pi over 2. In other words, from negative 90 to positive 90 has a difference of 180, which is my pi, right? This is 180 degrees. So if I'm at negative pi over 2, that's going to take me all the way to pi over 2 for my one completion of a cycle. So let's try to figure out our key coordinates here. We're starting at negative pi over 2, right? That's our starting point. And we want to divide up our period by 1/4. So because there's 4 points. Remember, we have our high point, which is our starting, then we hit the x-axis with cosine, then we go down, then we go hit the x-axis again, and then we go back up to the top. That's the cycle of a sine graph looking like this. Okay, did I say sine? I meant to say cosine. So if we take 1/4 of pi, that's pi over 4. Remember, that's 45 degrees. All right. So if I'm going to interact pi over 2, negative pi over 2, with pi over 4, I really need to get a common denominator. So we're going to think, rather than negative pi over 2, we're going to think of negative 2 pi over 4 as we plot out these points. So I'm going to write these below here. So this is equivalent to negative 2 pi over 4. So if I add a pi over 4 to that, which is the length of one of my 1/4 of a period there, we're at negative pi over 4 now. Negative 2 plus positive 1 is negative 1. And then if we do that again, we add another pi over 4. We see we're at, so actually let's do this here. So this was my second point here. So I'm going to write that in here, negative pi over 4. And then if I add pi over 4 again, that gets me 0. So that's my next spot here, 0. And then I'm going to add another pi over 4, which takes me to 0 plus pi over 4 is just pi over 4. And then one more time. Remember, there's a total of 5 with my starting point. We add another pi over 4. That gives me 2 pi over 4, which is pi over 2, which is 90 degrees. So I'm up to that. Actually, this was supposed to be pi over 4. Somehow I put pi over 2. I don't know why. Let's put the 4 back in there. And then my last one was pi over 2. So I'm at 90 degrees. And these are the 4 key points over which we will now graph our equation. Okay, so the key points that we found here started at negative pi over 2. I'm just going to write these down. Negative pi over 2. Then we went negative pi over 4. And then 0. And then pi over 4. And then pi over 2 again. So starting with our beginning, the 5 points that we had there starts at negative pi over 2. So notice that 0 here in this case is at the center. So if we want to keep track of where the actual y-axis is here, this graph that I have here will work perfect. And it will take into account the phase shift. So each one of these I'm going to give, so I'm actually going to use my units as pi over 8, so that every 2 I'm at pi over 4. So to get to negative pi over 2, we're going to go right there. And then my next one would be right here, and this is going to be my negative pi over 4. And then we'll go 2 out again. Again, you could choose different units. As long as you're consistent, you're going to be okay. I just like to give it a little bit of space if I can. And for 1, instead of using those units, I'm going to go up 1, 2, 3, 4. We'll just put 1 up here. So I'm dividing my units really into fourths. Each tick mark is a fourth, at least on the grid. And so I go up 4 to get to 1. And if I was doing, if our amplitude was anything more than that, I would I'd put that number there. I'd put 2 or negative 2 if we were dealing with that. Keeping in mind that we're dealing with a negative 1, we're actually going to start, normally I would start up here at positive 1. We would go from 1, we'd be at 0, we'd go down, we'd go back up, and then we'd end up here. But it's negative, so we need to do the opposite. So I'm going to put those dots in first, and let's change our color up here. We're going to do this. And remember, this is a curve. It's not a V that we want to draw. So as we go, we're going to smooth out those points there. And there we have it. We changed the period, we reflected it, and we shifted it. So we did pretty much everything there. All right, so let's look at a couple more examples here, practicing writing these out. The more you do this, the more that it becomes easier. Remember that with cosine, and we're going to start with A there. I'm going to write this up here, that it's A times the cosine, and it's my B, phase shift, and then X minus C, like so. And so those are the things I want to find here. And so the form that it's currently in, for me to try to identify the period, the phase shift, and I'm assuming we're going to do the amplitude as well, when we graph it, or if we're going to graph it, we first need to get it into the correct form. In other words, it needs to look like this. And so the one thing that needs to happen here is I need to be able to factor out 3. Because notice that B is not right in front of X, but behind a parentheses there. So if I want to factor out 3, I've got to factor out a 3 or divide this by 3 as well. And if I take pi over 2, and by factoring or dividing, if I divide this by 3, that's the same as taking pi over 2 and multiplying it by 1/3. Right? Multiplying by the reciprocal, which gives me pi over 6. So if I factor that out, we see here we factored it out. We know the amplitude here. We factored out the 3, and what I'm left with then is minus pi over 6. So identifying the period. First, the period is going to be 2 pi divided by whatever my b is. So that in that case, it's a 3. And so this is my period. I'm going to go from, well, that's my period. That's just going to be the length of it, right? And so, but let's identify the phase shift. The phase shift is, my C value is pi over 6. So that's going to move it to the right, pi over 6 units. So we are going to be moving to the right 30 degrees or pi over 6 units. And so if I want to think about what the interval is going to be, I'm going to have to take my period and add it to the starting point. So in other words, 2 pi over 3 here, this is my period. So if I was starting at 0, it would go from 0 to 2 pi over 3. But I'm not starting at 0, I'm starting at pi over 6. So if I wanted to find the interval, which it didn't really ask me to do here, so I'm I'm kind of improvising a little bit, doing a little extra. If I take 2 pi over 3 and I want to add 6 to it, I've got to get a common denominator, so I'd add multiply top and the bottom by 2, so that's 4 pi over 6, to which I would add pi over 6, which would give me 5 pi over 6. So the interval over which I would graph my single period would start at pi over 6 and would go all the way and end at 5 pi over 6. And if you think about that, we could find our points, right, by multiplying this by a fourth and then figuring out our points, and then we'd be ready to graph it. Okay, here's an interesting, another one with the sine. Again, notice that when we start out here, the sine is next to the x. I don't want it in this form, and I've got a 2 there. So I'm going to factor out the pi so that x is by itself as so. And then we would divide the 2 by pi. So if I redistributed this, I'd be back to where I started, right? Pi times 2 over pi just leaves me with 2. And they actually put in, since it's plus 2, so I could identify c correctly, they put it into the general form as well, which is a subtraction of a negative. And so c, we know, is that value here. This is my c. This is my b. And so my period is going to go from what would normally be for a sine function. This keeps moving. It would normally be 2 pi. We're going to go 2 pi over pi. And so my period is actually going to be 2. And my phase shift, I'm going to shift, since c is equal to negative 2 over pi, then, and you don't necessarily have to change that. They did that for us there, but we could have just as easily had it left as x plus 2 over pi, right? If we remember that it's going to go in the opposite direction, that c's value is actually negative 2 over pi, and which means we're going to shift 2 over pi to the left. And that would be our starting point. All right, well, let's go through a full-on graphing procedure here. And we've got a whole nother deal. And so the first thing first is we've got a number in front of x here. We've got to factor that out. So we factor it out. And pi over 2, we need to divide by 2 since we're factoring 2 out, which is the same as pi over 2 times 1 over 2, which gives me pi over 4. And so that's what I have left under here. Notice they just left it as x minus. That's fine. We know that that's a shift to the right because c's value is actually pi over 4. Our amplitude here is 3. Remember, amplitude is the height there. The period we see is 2 pi over 2, which is just going to be pi. So that's how long it takes us to circle through one cycle. Our phase shift is a minus pi over 4. Well, c's value is pi over 4, but that's going to be pi over 4 to the right. So c's value is pi over 4, which means we're going to go pi over 4 to the right. Notice that's the opposite of what I see. It's a minus pi over 4. So c's value is positive pi over 4, which indicates that we're going to move it to the right. And my starting point. So I'm phase shifting it to the right. So the starting point is going to be at pi over 4. And since this is a sine, I've moved to the right pi over 4, and I'm going to start at 0. With a point, they're asking us for an ordered pair. And so let's do the x values of our cycle. So for our cycle, and I'm going to clean this up a little bit here. We don't need this anymore. Remember, we're going to take our period and we're going to divide it by 4. Or another way to look at it is to take our period, which in this case is pi, and multiply it by 1/4, which is pi over 4. So each point is this is what we're going to add each time, starting at pi over 4. So I'm going to put my first starting point, pi over 4. We're going to add one more, pi over 4, which would give me 2 pi over 4, which is pi over 2. I'm going to write the simplified version down here. We're going to add another pi over 4, which would give me 3 pi over 4, which can't be simplified. Then we add another pi over 4, which would be 4 pi over 4. See how it's much easier if I keep that denominator there, but then take note of where it simplifies. And then we do one more, 5 pi over 4, which cannot be simplified. And these are my 5 points for my cycle. So as we look to graph it, I'm going to take into account. So as I'm looking to regraph this, or to graph this, I'm going to take into account the fact that I've shifted to the right. So my y-axis there, I'm just going to put on the far left-hand side, and that gives me room to go to the right there. And just like I did with the 1, I'm just going to go ahead and put 3 wherever I want to put it, and then -3. So here I put it 1, 2, 3, 4 units up. So I'm going to go 1, 2, 3, 4 units down. You don't have to do that. You can count to 3. I'm just doing it to give it maximum up and down. And keeping in mind this is a sine function that we're graphing. So it's going to start at 0. And I'm going to go every 2 units. I'm going to put one of my things. So we're going to go to the first one would be pi over 4 here. 2 more, then pi over 2. And then 3 pi over 4. And then pi. And then 5 pi over 4 for my last. The important thing is to label these so that we've chosen our units. Every 2 units is a pi over 4 when we've stayed consistent. And that's actually where I'm going to start with. This is a sine function. So as we go to graph this, 0 is here. It's not negative, so I'm going to go up then to 3 and get rid of that. And then down to 0, and then down to -3, and then back up to 0. There I have my sine function. If I had drawn a regular function, so say we had no shift there, but that 2 was still there, the original sine function would end at pi rather than pi over 4, and would go up to here, then down to here, and then down to here, and then back up to here. So we can see that we've moved all of our points pi over 4 units to the right. So we've shifted. You don't have to draw those in. I'm just drawing the original in as a visual. And of course, we knew this was coming. Now we're going to look at when we add something on the outside there. Of course, when we add something on the outside, we know that shifts it up and down, and it shifts it in the same number of units as where we started. In the same number of units as is written, right? In the same direction is really the big one. Why? Because in the general, unlike we had with C here, in the general formula, it is a plus. And so that tells me whatever D is, it's going to be very obvious to me. Whereas here, as I'm looking at the original graph, this is something we graphed a few slides back here, we see that C is equal to negative pi over 2. That meant it shifted to the left, pi over 2. And then we had 2 pi as our period. If we divided that by 2, we see that our period is pi. And then as we took 1/4 of pi, divided it up into the 4 units, each movement we're going to add pi over 4. So starting at negative pi over 2, that gave me negative pi over 2. Then we added a pi over 4. That took me to negative pi over 4. And then that took me to 0. And it took me to pi over 4. And then it took me finally to pi over 2. Hopefully you kind of remember this. I'm going a little fast through there. So looking at this, where my amplitude is 1, I'm not going to go as high this time because I don't have enough things. So I'm just going to put 1 here and negative 1 here. And let's sketch out the original function. So I believe I went by 2's. So we'll start back here at negative pi over 2. Then we had negative pi over 4. Then we had, of course, 0. Then we had pi over 4. And pi over 2. And this was a cosine, and I'm trying to remember if it was negative. I think it might have been negative, but this one is not negative. So I'm just going to graph what it is here. Start it off here, and then there, and then there, and then there, and then there. And doing our curvy thing. Remember, these are not straight lines that we are using here. It could have been a little less straight here, so let me retry that again. So coming out, we're going to go up and then a little more like that. Now I made it 2. I overcorrected. That's okay. So in actuality, shoot, I need to, if we're going to go up 3 units, I should have gone down a little bit there. So I'm going to just fix this really quick because I just noticed that it's 3 and not 2 that I'm aiming for. So I'm going to change the units along my y-axis there. All right. So anyway, I apologize. This will just take a second. 0 and then pi over 4 again here. All right. So this is what I'm going to put for my 1 and my negative 1. And then we can go 2 here and then 3 here. Okay, so I'm going to draw these out first. We're at 1, so we're here, and then here, and then here, and then here, and then here. So we flatten it out, but this is actually my standard one. All right, with adding 3, all that does is it shifts each one of these up 3 units. So I was able to do this here. And then notice that the distance it went was down to negative 1. So that's actually going to take me to positive 1, because from 1 to negative 1, that's, well, I went, get my pointer here, I went 1, 2, 3, 4. So here I ended up shifting this up 4, 1, 2, 3, 4. So I'm going to shift this up 4, 1, 2, 3, 4. So we're actually here at 2. And then at the low point, we're going to be here at positive 1. And then we're going to, because that also shifted it up 4 units. Then we go up to 2 again, and then we're up at 3. So my new graph here looks like this. Each of these units got moved up 3. And, yeah, there you have it. Now we're going to look at an example that actually takes what we have here and, a story problem that actually fits with a sinusoidal graph, and see if we can put it together. And what we've decided to use here, something that we know is cyclical, which is daylight hours throughout the year. And so we've got Paris here with the number of daylight hours in each month. I'm assuming we're picking a certain day in the month, probably the day where we have the highest number of those. And so anyway, we can see that the shortest day here is in December, and then the longest day, or the greatest number of daylight hours, is in June, when we have the solstice. And so looking at those two numbers, if we find their average, that's going to give me kind of the middle point. So 16.1 plus 8.3, if we divide that by 2, we get 24.4, which is 12.2. And so that's going to be kind of the middle area of my curve. And if we graph these out, we can see these on our graph. The January is just not quite at the lowest point here. We had the lowest point 8.3. We had the highest point 16.1. But the lowest point is over here, the highest point up here, and 12.2 here we have marked in the middle. So the distance that we go from the middle up to the top and from the middle down to the lowest, that's going to be my amplitude. And so that would be 16.1 minus the middle there, which is 12.2. And with that, we get, that would be 3.9. So that is my amplitude. Remember, the amplitude isn't the lowest to the highest, but rather the middle to the highest and the middle to the lowest. So that's my A value we have for this is at 3.9. We also know if this was a sinusoidal graph, it would be located at 0. And that would be kind of the middle area that we have here. And so this has been shifted up 12.2 units. So the D, which is the shifting up and down value, is actually at 3.9. And the period, well, that's a little bit trickier here. We do know that it's 2 pi over b, and b is what we want to find. But we know that this is over a 12-month period, right? Our units here are in months, so we need to figure out what our sort of trigger points are here with that. I'm getting all kinds of lines all over the screen. So let's solve this for b. If I take and put 12 over 1 like so, I can do a cross multiplication where I set them equal to, so 12b is equal to 2 pi. And so 2 pi times 1. And so b is equal to, oops, forgot the 2 there, is 2 pi over 12, which reduces down to pi over 6. So that is my period here that we're going to use. That's the value of b. So we could plug these into the formula there that we have for sine. We're going to go f of x, and I know that my amplitude is 3.9, so I have 3.9 times the sine, and that's of my b, which is pi over 6, times x minus c. We don't know the horizontal shift quite yet, but then we also know it's plus 12.2. That's my d value. So with this function, the one unknown I have yet is the c. That's what we are going to need to find. And to do that, whenever we have just one unknown, but we have some ordered pairs that we can use, let's go ahead and put in a value for x and y, and then solve it for c. We don't necessarily have to use the maximum value here, but this is what they are going to do here. They say at June 6th, we have 16.1, and that's our maximum value. So let's go ahead and plug that in. X being the month, right? Month of June is x equal to 6. And so we put that in. We have, that gives me 16.1 equals 3.9 times the sine of Oops. Now, why do they have, okay, I don't know why they put that extra parenthesis in there. I'm going to actually remove that. So we already have this parenthesis. So we have sine of pi over 6 times x minus c plus 12.2. So let's simplify this first by notice that this is all a big multiplication here. We have 3.9 times the sine of all that stuff there. So first we would want to subtract 12.2 from both sides. That's going to give me 3.9. Which is equal to 3.9 times the sine of pi over 6. Pi over 6 times x minus c. In dividing both sides then by the 3.9, that leaves me with 1. I'm going to put this over here. 1 is equal to sine of pi over 6 parentheses x minus c. Okay, so now I need to sort of get rid of the sine. And to do that, we take the sine inverse of both sides. So, a bit hard for me to write that in here. I'm going to put the sine inverse of sine. And so that gives me the sine inverse of 1. When we take the sine inverse, it will always give me something between 0 and pi over 2. So we look at it from the standpoint of the first quadrant. And of course, sine, which is my y value, is equal to 1 at pi over 2, so at 90 degrees. Also, this sine undoes that sine, and so we're just left with pi over 6 times x minus c. Now to get the x, or the pi, or I'm sorry, the x minus c by itself, sorry, that's not x anymore. We actually had a value for x that I did not put in there. I put in the 16.1, but I did not put in the value for x. And the value for x there should be a 6. So let me just go back and fix that little mistake. Some of you are probably going, excuse me, why didn't you? Well, I don't know. I don't know why I did that. I just got going there. And so I'm trying to take out all the x's there. And we're going to put 6 in its place. So that's 6 minus c. 6 minus c. And 6 minus c. Okay, so multiplying, we can get rid of this pi over 6. Actually, we can distribute that pi over 6, now that we know it's there, to both parts. Or we can just get rid of it. Yeah, I'm still just going to get rid of it. All right, let's just multiply both sides by the reciprocal of that to make it. So multiply both sides by 6 over pi. 6 over pi. That will eliminate this here and just leave me with 6 minus c. And over here, the pi's cancel, and I have 6 over 2, which is 3. And so if I add c to both sides and then subtract 3, we see that c is going to equal 3. So the full equation here for this, and this was a tricky one, is for this, we have y equal to 3.9 sine of pi over 6 times x minus 3, and then plus 12.2. Let's go back and look at our graph on the previous page. Actually, we might have it here. Nope. Previous page. So this is our shift. It was minus 3, so you'll notice this is the point here where the sine curve would begin. right? It began at month 3. That's where it was sort of at the middle point. And normally sine curves start there at 0. So 3 months was my shift to the right, and so that's why we have x minus 3. That indicates a shifting to the right of 3 units. So hopefully you've seen through this video here how we can use all of those things that we've looked at as far as when we multiply, when we add, when we subtract, if we're adding or subtracting to y, or adding and subtracting from x, or multiplying x, how all of those things will affect the basic parent functions of sine and cosine.